I'm the speaker for today. Okay, you all know me, so I don't have to introduce myself. And this is the topic of today's talk: AI coding, computer shaders versus CUDA versus openCL. All right. You have heard many good things about AI. Many good things. But at the end of the day, AI will get you nowhere unless you have what? Unless you have, guess what? Data. Big data. Big data, all right? And unless you have a good place to store that big data, unless you have an efficient way to process that big data, if you don't have those things, forget it. You may as well just kiss this whole AI thing goodbye. This is why Forbes and many other people regard data as what? The new gold. The new gold, all right? Without data, or more accurately, without ability to process the data, there's no AI, period. That is what AI is. It's the processing of huge volumes of data at warp speed. Huge volumes data at warp speed. Okay, so how huge? Just to give you an idea. The early version of ChatGPT, which set the entire world on fire, was developed using 175 billion data points. Huge? No. Because what? Now, every day, 2.5 billion bytes of data are created. Do you know how big quintillion is? It's 10 to the 18th power. 1 million trillions, okay? True? Yes. Actually, just in the past next few months, okay, data generated thanks to AI is expected to increase another 50%. Another 50%, all right? So, two questions. First, where in the heck are we going to put all that data? You cannot simply just let the data evaporate into the air. You've got to store that stuff somewhere. Currently, data is stored in large buildings called the data centers. Okay. There are more than 5,400 plus in the United States, okay? Data centers. However, these data centers are already obsolete because they cannot keep up with the speed data is generated. Okay. We need far bigger data centers, okay? Far bigger, okay? We call those far bigger data centers mega data center, okay? Each mega data center is 6 times more powerful than the current data center, okay? Currently, 300 plus are in development. More are coming. Okay. Who are building those mega data centers? Google, Meta, Amazon, Microsoft. Okay. All those companies are jumping into this in a big way, right? Just how big is a mega data center? Imagine the flight deck of a giant aircraft carrier, such as this Gerald Ford, nuclear-powered aircraft carrier. Okay. And then imagine 275 of them side by side. That's how big mega data center is. Okay. So remember, no data, no AI. Okay. No data, no AI, period. All right? These are some of the data centers, not the mega data centers, some of the data centers in the United States, all right? And this is one of the data centers in China, right? Now the second question, actually more critical question. How can we process these huge volumes of data? CPU cannot do this job. We must use GPUs. I'll explain why. Okay. First, note that ChatGPT is trained using 4,000 plus A100 GPUs. Okay. GPUs are expensive, all right? Very expensive, okay? 4,000 A100 GPUs cost $6.5 million per month just to rent, okay, just to rent. That is what, $76.8 million per year just to rent those, 4,000 plus A100 GPUs. All right, of course, then you would ask, why we must use GPUs? Modern CPU may have 4 or 8 cores, but the modern GPU can have as many as 4,000 cores, all right? These GPU's cores can run independently with their own input and outputs, right? Besides, overhead of creating threads on a CPU is very high. On the other hand, overhead of creating threads on GPU is relatively low, right? Well, the question is, GPUs cannot function alone, all right? They must work with GPUs more accurately, work under the control and the coordination of CPUs, right? So computing entered what? A heterogeneous era, okay? Because our systems now have multiple types of what? Computing power, cores, like CPUs, like GPUs, ASICs, FPGAs, and MPUs to achieve improved performance, all right? ASICs are widely used in data center, application-specific integrated circuit, okay? FPGA means what? Field Programmable Gate Array, and MPU is Neural Processing Unit, also called AI Accelerator or Deep Learning Processor, okay? But what exactly are the roles of the CPU and the GPU? Okay, here is a conceptual structure, okay, of a heterogeneous system. Okay, the CPU, I mean the C++ application, okay, through some API, okay, send commands, send data to what? To GPU. Actually, GPU cores, okay. And GPU cores will execute the commands or the tasks, in parallel using the provided data, data by the CPU. And then result of those GPU cores will be sent to CPU again, okay, for for updating, of the screen or further processing. So this is a standard, very simple heterogeneous system. Okay. So basically, we are looking at 5 stages. Okay, interaction. Okay, the CPU send a command to GPU. The GPU process the command, and then the CPU sends data to the GPU, and then GPU executes the command, and then send the result back to the CPU. All right. So currently, well, not currently. Okay, used to be this way here. The first stage, going this direction here, sending commands to GPU, and GPU process the commands, and then CPU sends data to GPU. GPU process, execute the tasks or the kernels, and then send the result back to CPU, right? But actually, CPU and GPU now are integrated into the same chip called the APU, all right? The so-called accelerated process unit. And the communication between CPU and GPU now is done by a piece of hardware called PCIe, all right? Which stands for Peripheral Component Interconnect Express, right? But what is CUDA? What is openCL? And what is computer shader? Right? These are parallel computing frameworks and APIs for using GPUs. Okay. Let me give you a little history here. Okay. In the not too distant past, slightly more than 20 years ago, the only way to program GPUs was to use what? GPU assembler. Okay. That is very difficult and, most importantly, boring work, okay, if you know assembler, all right? So the openCL folks gave us what? A higher level language called the GLSL, okay, which can be considered as very rough API level above the assembler level, above the assembler level, all right? So application is easier, but not that much, not very much, okay, not that much. GLSL stands for openCL shading language, all right? But parallel processing on GPU was not the focus then, Okay. Why? Because the number of cores on GPU was not massive yet, okay? Was not massive yet, okay? However, when the number of cores built into a GPU became bigger and bigger, okay? 100 cores, 200 cores, 500, 1,000, 2,000, 3,000, 4,000, and now even more, okay? People started to realize the power of what? Of a GPU is beyond just rendering, all right? Actually, beyond their imagination, all right? So APIs were developed to utilize what? Utilize this tremendous parallel computing power of GPUs for other applications. Well, actually, mainly for AI, Okay. So nowadays, this is what we have. Okay. We have what? We have a better API label. Okay. Instead of just this very primary GLSL. Okay. We have better API label now. Okay. with what? With CUDA, with openCL, with computer shader, right? Don't worry about this structure here. I'll show you, each of these in detail shortly, all right? So let's consider the case of CUDA first. Think of CUDA as what? Think of CUDA as an extended C, C++, okay, that allows software to execute the functions on the GPU using many threads in parallel. So CUDA actually included C, C++ as what? As a software, as a language. Right? So this is where CUDA is. CUDA deal with what? GPU assembler directly, okay, directly, all right? However, graphics applications are important. So CUDA can also, handle graphics applications, okay? Using what? Using openGL through GLSL, all right? So CUDA includes C++ as a subset, but it can also go through this path here, all right? Can also go through this path here, okay? This is modern GPU, all right? So if graphics work is needed, CUDA can also go through this path here, all right? So let's see how CUDA converts sequential operation like a vector addition to parallel operation, okay? So to perform, addition of two vectors, arrays, all right, A and B, if we use CPU, you have to do this sequentially, right? Now, CPU could have, 4 or 8, cores. Therefore, we can break this, 16 sequential operations into 4, parallel operations, okay? If we use CPU cores. Well, this of course is not, as good as, doing, all the addition for all the 16 entries in parallel, okay? Well, of course, in that case, we need to have what? At least 16 cores for each of these, array entries, all right? So that's the purpose here. That's the purpose here. So let's use a hello world type CD CUDA example to explain the process here, all right? So the process involves what? Okay, remember the 5-stage, process, okay? Declare and allocate host and device memory. Host means CPU, device means GPU. And you initialize host data, okay? You transfer data from the host to the device, and then execute one or more kernels. Kernel in this case means what? A task or a function, okay? Sent from the host to the device. And then, once the parallel work is done, then transfer result from the device back to the host, all right? So here is a very simple example, all right? Part 1, okay? So you have to define a kernel or a function to perform the so-called what? A plus B. Only that, this will do, the addition for each entry or for each, each part of the array in parallel, right? We use APB, array A plus array B, to represent this function here, right? So here is, this function or this kernel here. Don't worry about this. We'll go back to this shortly, all right? And CUDA use this global underline, okay, declaration specifier to what? To define all those kernels. So anything defined after this, will be, a kernel sent to what? sent to the GPU cores, all right? All right, and we have to declare CPU arrays, okay, and we have to declare GPU arrays, okay, separately, all right? You declared CPU arrays using using C++ command, all right? And you have to use CUDA command here to define or to declare your GPU arrays, okay? But all this, are done within the CUDA program, okay? Okay, and of course you have to initialize the CPU arrays, okay? So, and here is part 3, all right? You have to, transfer data from what? From your CPU arrays to your GPU arrays or that device arrays, all right? And you have to, even it's just one step, actually, this is, the most critical, step of the entire, CUDA program here, all right? You have to launch your kernel function, okay? I'll go back to this thing shortly, too, all right? Once, the parallel work is done, then you simply send the result back to what? From the device array to the host array, all right? Okay. If you want, you can do some, further processing on this result here, such as this part, very simple, error checking steps, all right? So transfer data from device to host, the last stage in the 5-stage process, all right? And then once your work is done, then you have to free those CPU arrays using, data arrays, those device arrays using CUDA command, and then, free those CPU or host arrays using C++ command, all right? So the concept in the flowchart is very simple, right? Very simple, okay? Here's the configuration of GPU cores, okay? CUDA divided the GPU cores into grids, and each grid, contains several CUDA call them thread blocks, okay? So in this case, each grid here contains 4 thread blocks. So thread block 1, thread block 2, thread block 3, thread block 4, right? And we have only one grid here, all right? Only one grid here, all right? So here is the execution configuration, all right? You have one grid, and this grid contains 4 thread blocks, all right? You have, remember that, this is how you launch this kernel, right? How you launch this kernel, okay? This part tells the system, okay, we have how many thread blocks. Let's go back to this simple thing again. Initially, we define our n, all right? By doing a left shift for 4 bits, okay, you get, your n is set equal to what? Your n is set to equal to 16, right? So remember that you have a variable, okay, whose value is 16, right? 16 also is what? It's the size of array A, size of array B, and the size of array C, all right? So this is where the kernel was launched, in what? In the CUDA program. APB is the what? Is the kernel or is the function. And this part here tells the system that each grid here contains what? Each grid here contains 4 thread blocks, okay? And this part tells the system each thread block has how many threads? 4, all right? 4, okay? And we have 16 threads, all right? And we use DA-DB-DC as what? As the CUDA arrays or the device arrays, okay? So APB, of course, will get this part, all right? Get in, get DA-DB-DC, right? So APB get this part here from what? From the CPU, okay? So this is what? This is the GPU kernel. This is the function that GPU will receive and then will what? Will execute, all right? So what this part is, this part tells, okay, which thread block to use, okay? And for each thread block, we have 4 threads, right? And this part tells, okay, which thread in that thread block should be set, okay? It should be set, all right? So if we use, for instance, this has to be 0, 1, 2, and 3. So when thread block 2 is reached, okay, we have to multiply this by 4, and then if this is set to 0, of course, then we get what? We get thread what? Thread 8. This 8 here is also what? It's also the entry of the array that will be performed by what? By this thread here. And all this will be done in parallel, okay, in parallel, right? So this is what? So this is the work that, well, in this case, of course, it's just one addition, but could be a set of operations, okay? So once you have this simple program here, then of course remember that CUDA includes C, C++ as a subset, all right? So you don't use command, you use CUDA command, okay? So you save the code in a file with a .cu extension. Let's call this apb.cu. And then you use the CUDA command to compile this program. You don't use G++ or GCC. You can use NVCC. NV, of course, means NVIDIA, all right, to compile this CUDA program, and then execute this program, and this line is the output of what? Of the CPU. So this is how a CUDA program works, okay? You get what? You get the data from the CPU, you get a command from the CPU, and then the CPU, and then the GPU cores execute all those, the kernels, in this case only one, in parallel. And once the execution finished, then send the result back to what? Send the result back to the CPU, okay? Doing this using computer shaders or openCL is similar. This here means what? Of course, converting single operation to pure operation, all right? There's a typo. Compute shaders kernels are programmed not the same way. It's programmed in GLSL, okay? So this is a relationship between the computer shader and your application. They are independent, okay? Therefore, your computer shader program has to be compiled, separately. In the CUDA case, okay, you only have to compile the CUDA program, all right? In the openCL kernel, openCL stands for Open Computing Language, all right? OpenCL kernels are programmed in a C-like language, similar to GLSL, all right? Therefore, programming OpenCL is similar to programming shaders in OpenGL, all right? So for openCL, okay, the openCL program has to be compiled separately. Okay. 2. So consider the case of what computer shaders now, right? A computer shader is a variant of openGL shaders, but it's not a part of the openGL pipeline. It runs independently and has no predefined input or output. Okay, so here is a relationship. Okay, your open shader here, okay, is built on top of what? Built on top of GLSL. Okay, but it doesn't have to go through the openGL pipeline. It doesn't have to go through the openGL pipeline. Okay, we're not doing graphics. Okay, when doing graphics, it can and will go through the openGL pipeline. Okay, this is the openGL pipeline here. Your application has to create a vertex shader. Your application has to create a fragment shader, and these shaders then will go through what? Send it to the pipeline with what? With results from GPU. Okay, okay, for rendering purpose. Okay, for rendering purpose. Well, if you do not do graphics, then your compute shader does not have to go through this pipeline here. Okay, but it will go through. Okay, naturally, if necessary. Okay, so here is very simple, compute shader program. Okay, for pair computing. Okay, we don't use 16 entry array. We use a 6 entry array here. Okay, so all this will be done in parallel, right? Obviously. Okay, so to run a compute shader program, okay, we need to know how to create a compute shader program and how to specify the buffers to be used for and by the compute shader program, right? So here is a very simple, program. 2, okay, you have to declare your buffers. I explained to you why we have to declare buffers, and you have to set the link to your computer shader program. We call this link SCS here, simple computer shader. Okay, and you have, of course, you have to declare your arrays A, B, and C. Okay, these are host arrays. Okay, and then you have to create a computer shader for the specified files. Okay, so you have to call this function of this header header function here to get this thing compiled. This is done during runtime execution time of your C++ program. Okay, and then you have to declare your what? Your buffers. Okay, your buffers. Okay, buffers for sending results to the computer shader program, and then buffer for what? Buffer for sending result from the computer shader to what? To the host. Okay, to the host or the CPU. Okay, so here is the difference for a computer shader program. Okay, the host arrays and the computer shader arrays, they don't communicate to each other directly. They have to do this through what? Through buffers. Through buffers. These are openGL buffers. Okay, so here we follow some openGL protocol. All right. Okay, so that way, computer shader can go through openGL pipeline naturally because we follow the protocol of openGL. Okay, so remember that for a computer shader program, host arrays and device arrays do not communicate directly to each other. All right. All right. Then we also need to know how to activate a computer shader program, how to bind the buffers to be used for and or by the computer shader program and how to specify the number of worker groups to be invoked. Okay, in in computer shader, we don't use the name shred block. We use work groups, but they are the same thing, exactly the same thing. All right. So, part 2. Now you have to define this function, computer sum. Okay. Okay. Initially, you have to set, SCS as the current computer shader for execution. So set up your computer shader program, okay, and then specify both the buffers and the associated index. Remember, buffers are something in between the host arrays and the device arrays, okay? And then you what? Well, first this part, but we have to bind the buffers, okay? And then we have to tell the system, okay, where to get the result. In this case, of course, sending the result from the device to the host, okay? Through what? Through buffer 2, okay? But most importantly, again, this is just one step, okay? One step, okay? First, you create what? You create 6 copies of what? SCS program, all right, or the kernels, okay, and perform array addition in parallel. We haven't seen the computer shader program yet, but this part is similar to CUDA. Okay, you have to launch your what? You have to launch your kernel, all right. In this part here. Remember, this is the first step, okay? This program then will be executed, all right, by 6 GPU cores, okay? By 6 GPU cores, okay? So create 6 copies of the SCS program here, all right? And this part simply tells the system that ensure the computer shader finish before proceeding. Okay, so it's a prototype, protocol thing, type of thing, all right? And then this is your main program with your, application, C++ program, okay? So you need core computer sum, okay, to what? To launch the kernel, right? And then once the work is done, once the result has been sent back to the host, then you can do some, further work. Here we simply output what? Output the result to screen, okay? Output the result to screen, all right? So here is the computer shader program here, all right? Computer shader program, okay? Stored in what? Stored in this file, scs.glsl. This is written in GLSL, okay? So first, we have to tell the system each work group has, in this case, only one member, all right? And then, okay, we have to declare the input arrays and the output arrays, all right? Then this will be called by what? By the computer sum, okay, function of the application, okay? And here it will, in this case, of course, just we'll do one thing here. Get ID number for what? For the worker group members, okay? So in this case, each group has only one member, right? And then we get work group number for each of the 6 entries of an array, and then perform this array addition in parallel, okay? So remember, computer shader code, are compiled separately, okay? So you call the GCCs to compile your application, and when the application is executed, okay, the shader program then will be compiled and then will be executed, okay. So the execution is the same. This is the output you would get from from the CPU, all right. In openGL, host arrays and the shader arrays communicate through openGL buffers, all right. In openGL, host arrays and shader arrays, for other shaders, they don't communicate directly through buffers, okay. So computer shaders are, defined, follow the same protocol, okay. That is why computer shaders can go through the openGL pipeline naturally, because this protocol is followed, all right. So as for openCL, okay, for openCL, it deals with GPU assembler directly too, but it can also go through what? Can also go through the openGL pipeline if graphics work, is needed, okay. So like I said before, programming openCL is similar to programming shaders in openGL. Therefore, we have no need to illustrate the process for openCL, okay. Now, overall, which framework is a better choice for AI coding? Computer shaders, CUDA, or openCL? One answer is to ask ChatGPT. I'm just kidding, all right? I'm just kidding. CUDA was developed by NVIDIA, owned by NVIDIA, all right? So it's a proprietary format, okay, of NVIDIA. Since it deals with GPU assembler directly, so it needs extra drivers to work with CUDA, all right? And the CUDA runs on NVIDIA CPUs only. This doesn't seem to be a problem at this moment because NVIDIA GPUs dominate, 80 to 95% of the market. Okay, so most of the people, use NVIDIA GPUs, all right? So of course, CUDA can work on those GPUs, and CUDA can, take care of multiple different kernels. Okay, for each application, you can have several different, kernels. Okay, running in the same time. Okay, all right. For computer shaders, okay, computer shaders can work on any GPU that supports OpenGL 4.3 plus. Okay, and this is the case these days, except what? Except Mac computer. Okay, Apple computers does not support OpenGL. Once you know the protocol, or the communication protocol between host and device, the implementation of computer shader program is actually quite straightforward. All right. So the only difference is that the protocol, the communication protocol is slightly different. That they don't talk to each other directly. They have to do this through the so-called buffers. Okay, that's the only difference. Okay, and computer shaders are suitable for people who connect computing with drawing frequently, because it's built on top of what? GLSL. Okay, and it goes through OpenGL pipeline quite naturally. Well, and it also supports multiple different kernels. Okay, for OpenGL, it also runs on all GPUs. All right, coding is similar to programming shaders in OpenGL, and it also supports multiple different kernels. Okay, So multiple different kernels can also be executed in parallel. Okay. By the way, that openCL was originally developed by Apple. Now it's supported by AMD, IBM, Qualcomm, Intel, and NVIDIA. All right. So here is my recommendation. Either one is fine. Either one is fine. Okay. CUDA, computer shader, or openCL. However, CUDA and computer shader seems, to be a little bit more popular. Okay, but you have to know the minimum AI coding requirement. Okay, on one side you need to know Python or C++ on the code side. Device side, you need to know one of these three APIs, okay? Computer shaders, CUDA, or openCL. I didn't say which one is better, all right? It's up to you, okay? But remember, openCL, or Mac computer does not support openCL. But because of the success of Sora, developed by OpenAI, big companies like Amazon, Google, Meta are all developing similar products to compete with Sora, all right? Besides, not to mention those companies whose business involves images, pictures, extensively, such as TikTok, such as Adobe, such as YouTube, all right? So people who are good at connecting computing with drawing would, and I believe, should have an upper hand. You know what I mean, right? You know what I mean. So this is my presentation. This is the end, all right? Any questions? Any questions?
So the example you gave is like you let the GPU do addition, add to numbers. Do GPU can be programmed to do general computation like all the loops or the branches or multiplication of real number, or all those things? Or do you usually do? Or
those loops, they can be declared in your application.
So the control is still in the CPU, then the GPU is just
when you need to do those real work, you can send that work to GPU.
Okay.
Yeah, this is more of a comment than a question, but just kind of two quick things. One is that openCL, I'm not sure whether you were aware of this or not, but openCL has also been used very widely to target FPGAs. So now, rather than writing things like Verilog code for custom accelerators, you'll find that there are a lot of people actually just taking their OpenCL code and using that. The other thing that's kind of interesting is that there's a new fastest machine in the world as of 6 months ago. That's El Capitan. And El Capitan.
All right.
And El Capitan is AMD based, so it's all AMD GPUs.
AMD GPUs.
Yeah. So
So
there is some pressure at the top now for having a better environment for programming those.
But the AMD's market share is relatively small.
That's true because they haven't had a stable programming environment. For example, for about 2 years, they were actually supporting a compiler that would translate essentially the back-end code from CUDA so that it would run on AMD GPUs without any changes. But then they stopped supporting that. They've actually gone through about a half dozen different programming models, with each of them lasting just a few years, and that's kind of why they're in trouble, because NVIDIA kind of got a later start than AMD did. Well, I should say than ATI, which was then bought by AMD. But NVIDIA has had the same programming environment for all of this time, whereas AMD has gone through a whole fleet of different programming environments.
I believe that AMD's inference or impact on GPU is smaller, but AMD, had the impact or influence on CPU part is much bigger.
Well, AMD, or I should say ATI, which AMD bought, ATI actually built the first GPU that was not intended for doing graphics. So NVIDIA was actually a little bit later to the game. It's just the model that AMD had back then, or I should say ATI had back then, was something called CTM, close to the metal. And that programming model lasted about 1.5 years. And they've gone through a whole pile of different programming models. And their hardware is actually very competitive with the NVIDIA hardware, and usually much cheaper than the NVIDIA hardware. But as I say, this lack of a stable programming environment has been a big problem.
All right, I consider this as a comment. Any other questions? Well, if you don't have further questions, I would want you to watch a video clip here. Some of you might have seen this before. This never happened. This is my comment, all right? One should keep a low profile, never show off, right? Remember, this never happened. It's an AI product, all right? So, see, never happened. And yet, if you don't know anything about this, you would think that, did they really did this? Did they really do this before? That's AI. All right? That's AI. All right, so this is the end